Yeah, and then we have biclusters with constant column values. So the cluster model is now a little bit different. It says that we have a constant value, and but we have an adjustment for column J. Yeah, so within each column they are constant, but over the columns you have an adjusting value, so to say. Yeah, so and you see it here in this column they are all the same, in this column they are all the same, but now they need not to be the same all over, but this characteristic value can be different per participating column, per participating feature, as you see here. And this is the non-relevant feature, non-participating feature. Yeah. This results in an axis parallel subspace cluster because you see here they need not to be now identical. Well, they are still identical. I'm sorry, they are still identical if you project all those points on the participating attributes, of course. But they are now not necessarily on the bisecting line or plane, but they are somewhere. So they need not to be 1, 1 or 2, 2 or so, but they can be different, as you see here. Yeah. And again, we will have a look at the parallel coordinates here in the interpretation. So the points are located on the same values, again, like the constant biclusters, but not necessarily on the bisecting line as we had before. Yeah, because those values can now be different per column and not within the column. Yeah. Okay. And here is the parallel coordinate visualization. So you see here that again they should be similar. So this should be one line actually, and they spread here all over. But the line now is not necessarily constant anymore, but it can be up or down or whatever. No problem about that. Yeah. So yeah, again, I think a quite nice and intuitive model. Again, quite simple actually. Yeah. And the next one is also quite simple, which is not constant column, but constant row values. Yeah, so here is the model. Yeah, we have the same model actually. So every value is the same, but for different rows, we may have a different adjustment value. Now it's the adjustment value. That's why it is an R now, is now different for different rows. So you see it here. Well, if this is fixed, it's all fixed over all columns, all participating columns, but it can be different for the rows, as you see here. Yeah. And the result is that points are building a sparse hyperplane parallel to the irrelevant axis, which is similar to axis parallel subspace clustering. Yeah. So here is an example, and if you imagine that, well, they are somehow in here and along this. They are somehow on a plane which is parallel to the to A3 in that case. Yeah, so they are on a plane which goes something like through the data space like this one, like this here, parallel to A3 actually. Yeah. Okay. In the subspace, in the relevant subspace, as you see here, the points need not to be similar. But they are on the bisecting line of the participating attributes. Yeah? That looks a little bit like a correlation cluster, but it's not actually, because if you take into account any other feature which is not relevant, then they are just spread all over. So the hyperplane is, so this is the projection of the hyperplane those points belong to on the A1, A2 space. And this hyperplane goes up out of the screen, so to say, yeah, comes right into your face, parallel to an axis A3. If A3 is just coming out of the plane here, coming out of the screen, so to say, yeah. So that those are axis parallel clusters, or at least they look like axis parallel clusters, even though in the relevant subspace those points form a different pattern, because they need not to be very similar, but they are on this bisecting line. Yeah? So this is the characteristic pattern in the relevant subspace, which is somehow a little different than our traditional notion. Because our traditional notion says in the relevant subspace they should be very similar. They need not to be similar, they just need to be on the bisecting line. Yeah, visualization using the parallel coordinates. You see here now those lines are parallel to each other, but they need not to be the same. Yeah? It's like the constant values, but the constant values would be just one line, and now the lines can be shifted. Yeah, and again some arbitrary spread in A3 here. Yeah. Okay. So now we're getting a little bit more complex. Now we get biclusters with coherent values. So we now just take both things. We allow some adjustment in the rows and some adjustment in the columns. So we still have some kind of base value, the mu, but we allow adjustments both in the columns and in the clusters, as you see here. So it could be 1, 2, but the adjustment should be the same. So if we adjust 1 in this direction, we need also to adjust 1 in this direction, and again and again. Yeah. So those are those R, I's and CJ's. Yeah. The special cases obviously are constant rows if CJ is 0, and constant columns if R, I is 0. Yeah. Then we are in the cases we just had right away. Yeah. So what is the result? Well, the points are located on a hyperplane parallel to the axis of the irrelevant attributes. And again, this means nothing else than they are axis parallel subspace clusters in a sense. But again, the pattern in the relevant subspace, as you can see here, is again not necessarily what you expect, but again something like on a common line, which need not to be the bisecting line anymore, but they are increasing. They are on an increasing, well, not one-dimensional line, but if you have k attributes, k relevant attributes, it's an increasing k minus one-dimensional hyperplane in the relevant subspace. And again, if you add an A3 coming out of the screen here, those points would be on a hyperplane, which is this is the projection on A1 and A2. This would be the projection of the hyperplane, and the hyperplane just it comes straight out of the screen into your eyes, parallel to A3. Yeah? So that's why it is kind of comparable with an axis parallel subspace cluster. Yeah, and visualization here, it's kind of mix, obviously, between this and this here. So the lines are again parallel, but they can be shifted again. Yeah? They need not to be the same like constant rows, but they can be shifted. Yeah, and again a spread all over for the non-relevant attributes. Yeah. Yeah, and the last one here, which is probably the most complex one, is coherent evolutions. So for all rows, all pairs of attributes change simultaneously. For example, in the discretized attribute space, coherent state transitions, similar to grid-based axis parallel clustering approaches. We had that already, and but it could also be a change in the same direction, irrespectively of the quantity of the values of the change, actually. Yeah. And here is an example where you see here, okay, from A1 to A2, it's always the same quantity of change, over all those things here. Yeah. And how do those things look like? Well, it's a little bit different. They are points basically in a certain grid cell like half space. So in this example here, it's more or less something which is in this kind of half space. Yeah. That's why it looks quite similar to grid-based clustering, actually, to grid-based subspace clustering. Yeah. Again, the size of the grid could be a little bit bigger, so it's not a thing of density, a notion of density, but more a notion of some pattern appearing in the data matrix, which we try to relate somehow to the notion we had before of density. But as you see, it's not always directly related. Yeah. And the visualization of the parallel coordinates is in that case, all the lines between all the relevant features, they cross the border between the states, yeah, in the same direction actually. Yeah? So all those here have the same direction, but they need not to have the same slope. Yeah. So yeah, that's it basically. Yeah, and here they can be again all over. Some goes down, some goes up, some goes down, some goes up. But here they are all going up, or if there's another participating attribute, they all go down. Yeah, probably or potentially with a different slope. Yeah, and last but not least, change in the same direction is again coherent evolution. So the general idea is find a subset of rows and columns where a permutation of the set of columns exists such that the values in every row are increasing. Yeah, so you see here again that the rows are increasing, the values are increasing if you find the correct permutation, which is easy to, here, of course. Yeah, but anyway. In that case, clusters do not form a particular subspace, but rather a half space. Yeah. Here's the example with a change in the same direction. Could be in the different direction. So it could get smaller. It could get larger. So anyway, you know. And again, points are in certain half spaces. In that case, they are above the bisecting line here. Yeah. And if they are, if the values decrease, they are in the lower half space here, below the bisecting line here, in the relevant subspace. Of course, it's a bisecting hyperplane. Yeah, and the parallel coordinates just you see again that the lines are all increasing, and need not to be like this one here, cross somewhere. Yeah, so that they are all crossing. All lines cross border between states, yeah, in the same direction. And now here the border crossing is not valid anymore. Yeah, so they can be anywhere, but all lines are increasing or decreasing depending on the pattern, of course. Yeah. Yeah, that's it. Just to wrap up the cluster model before we talk about the algorithms. Here's the big picture. So we have the cluster model in between. We have the matrix pattern, which is actually the idea of the model, and we have the relationship to the spatial pattern. We talked about it, and well, it's just what we talked about it. So constant biclusters, no changes of values, axis parallel located on the bisecting line. Then we have constant columns and constant rows. Constant columns are axis parallel, constant rows are axis parallel sparse hyperplanes, coherent values and coherent evolutions. Yeah, and you see the relationship to the spatial pattern, and you may notice also here that the higher it is here, the more specialized it is with respect to the matrix pattern. Here there is no order of generality in the spatial pattern because they have been designed or have been defined by a specific matrix pattern. They didn't care too much about the spatial pattern. That's what we try to relate here in order to get you a better feeling of what those models are actually doing.